Good evening. We are going to start on synchronous motor drives from today's lecture. The basic coverage is going to be somewhat like this. We'll start with an introduction for the synchronous motor drive. And after that, we would be looking at starting, braking, and speed control. So in starting, we would be looking at some of the conventional methods, and we definitely need to look at something called hunting phenomena in synchronous motor drive. And as far as braking is concerned, most of the times in synchronous motor drive, what we employ may be dynamic braking, that is connecting a resistance right across the armature of a synchronous machine. That is dynamic braking. Another one which is very commonly employed in electric vehicles is regenerative braking. That is the machine which is working originally as a motor that will start working as a generator, and that is essentially going to feed back the power to the battery, because in most of the electric vehicles, it may be battery that is actually the source of energy for driving the vehicle. So regenerative braking may be employed. And speed control, we will mainly be looking at two different methods of speed control. One is variable frequency power supply. So variable frequency, variable voltage fed synchronous motor. So that means this is going to be VSI fed synchronous motor drive. So this generally is called as true synchronous mode. So the frequency is going to set exactly what is going to be the running speed of the synchronous motor drive. So this is generally known as true synchronous mode. The second type of operation where frequency will not be an independent variable. Here, essentially, frequency is an independent variable in the case of true synchronous mode. In the other case, it is called self-control or self-controlled mode. So in self-controlled mode, the rotor speed is going to be sensed and correspondingly the frequency will be set. So the frequency will not be an independent variable. So in this particular case, we will not be able to set the frequency independently. So how the control is implemented, we'll take a look maybe towards the end of this particular discussion on synchronous motor drive. So we had seen in detail about induction motor drive. So let me try to compare the synchronous motor drive and induction motor drive. So if we compare what is exactly the similarity or difference between the induction motor drive and synchronous motor drive, let me just recall once again the basic working of a synchronous machine. The stator is exactly similar to that of an induction motor. So we are going to have a phase here. I'm showing two-pole synchronous motor or two-pole induction motor stator. The stator structure is extremely similar. If I call this as A dash, I can call this as C and C dash. And I'm going to call this as B and B dash. So this is the way the windings are arranged. So when we supply A phase, B phase, and C phase currents that is time displaced currents to the three-phase winding, we are going to see a revolving magnetic field that is being set up like this. So this is the revolving magnetic field that has been set up. So once the revolving magnetic field is set up, if let us say I have the rotor here, let me show the rotor somewhat like this. So this is what is my rotor, two-pole rotor. So if this is the rotor and the shaft is attached somewhere here, so let us say if this is the two-pole rotor and I'm going to have the revolving magnetic field somewhat going around like this. This is probably the North Pole and this is going to be the South Pole at any instant of time, and this is going to rotate at synchronous speed. Then this rotor, which is made up of a piece of iron, or it is going to be made up of some permanent magnet, it is going to be dragged along with these revolving magnetic field. So the basic working is somewhat like this. Three-phase currents given to three-phase stator winding. So this sets up a revolving magnetic field in the air gap. Okay. Now what is going to happen is the rotor, which is made up of a ferromagnetic material or an electromagnet. Electromagnet means you may have a rotor winding to which you will supply DC, because of which this iron will become like magnet. So it can be an electromagnet or it is going to have permanent magnet material. So that is going to be made up of this, will be dragged along by the stator magnetic field, stator's revolving magnetic field. So once the rotor locks up with the stator's revolving magnetic field, the rotor is also going to start rotating, and this will also rotate at the same speed as that of revolving magnetic field. So if I call this speed as ns, which is the synchronous speed, now this speed is also going to be ns. So in this particular case, we are going to have stator magnetic field speed, which is equal to synchronous speed, that will be same as the rotor's revolving speed. So the machine will run, the rotor will run only at synchronous speed and not at any other speed. So this is going to be synchronous speed. It is very different from induction motor in that sense, because in induction motor, the rotor will always rotate at a speed which is slightly less than synchronous speed. That's where the slip comes up. Whereas here, we are not going to have any difference whatsoever between the stator revolving magnetic field speed and rotor's rotating speed or rotational speed. So here, the entire mechanism is dependent upon the locking up of the rotor and the stator revolving magnetic field. These two have to lock up with each other. That is extremely important. And if we are saying that the rotor can have either a ferromagnetic material or a piece of iron, or it can have an electromagnet, or it can have a permanent magnet in the rotor, this actually gives rise to different types of synchronous motor. So there are different types of synchronous motors that are normally seen. The first one is when we have an electromagnet. So we call this as wound field synchronous motor. So in wound field synchronous motor, which has a wound field rotor, the rotor is going to have a winding. So rotor has a field winding excited by DC. So you're going to have generally a field winding which is excited by DC. The field, if I'm looking at it, so I can have, let us say, this is, say, the stator, the rotor structure. So this is going to be one of the poles and this is going to be another pole. And I can have simply, I can show the winding somewhat like this. This is the winding to which I'm going to supply a field current. And because it is in the rotor, clearly, I can't have terminals directly connecting to the field supply or DC supply. So I have to have something like brush and slip ring arrangement. So unless I have slip ring and brush arrangement, I am not going to be able to supply DC to this wound field synchronous machine. So invariably, the field supply will be only about 220 volts or 400 volts or 600 volts, not anything more than that. Whereas if you look at the stator side, the stator will have at least kilovolts rating of power supply. It can be 11 kilovolts, it can be 1.1 kilovolt, or it can be 440 volts if we are talking about a normal three-phase synchronous machine. Whereas if I am looking at rotor will have only 220 volts DC or 400 volts DC and things like that. So the current carried by the field winding, that is going to produce the field flux. And that field flux is the one which is actually manifesting itself to produce a generated voltage in the case of a generator, or it is going to play an active role in magnetizing this rotor, rotor poles. So it plays a very vital role in making sure that adequate amount of magnetic flux is produced. So the current, whatever we supply, that can be quite high. So there can be multiple parallel paths of slip ring and brush assembly in many of the synchronous machines. Okay. So the field, what we are looking at, if it is going to produce, say, North Pole and South Pole, it doesn't even have to have any protrusion like this. I can just have a cylinder, but I can supply on this side positive current completely. And on the other side, I can supply the return current, or return current can flow through the other side. So in which case, this side will look like it is North Pole and this side will look like it is South Pole. So this is going to be the kind of arrangement where I am talking about a DC being supplied to the rotor. I can still have the rotor in a cylindrical structure. That is, this is the structure which I can imagine as though it is going into the board, something like this. Okay, so this is the rotor, whereas the stator will be surrounding this. So around this, I will have the stator sitting here. So I will have again along the periphery, inner periphery of the stator, I will have A dash, C dash, and B dash. This will be the kind of winding I'll be having, and you can imagine as though this is also going into the board, somewhat like this. So This will be the stator, whereas this is going to be a rotor. And although the rotor is cylindrical in structure, because I'm creating distinctly north pole and south pole by appropriately pushing the currents through these conductors, this will be attracted by the revolving magnetic field and dragged along. It's not a problem. So this kind of structure is generally known as cylindrical pole. So this is essentially cylindrical pole, and cylindrical pole is essentially being dragged along with the revolving magnetic field because of the polarity of the current what I have given to the windings of the field winding, which is residing inside the rotor. Okay, whereas the shaping of this rotor can also be done somewhat like this. I can have the rotor shaped somewhat like this. So I can have this as protruding shape. So this can actually be somewhat like this. So what I have shown here, this is going to be protruding wherever the windings are arranged, and it is going to have a larger air gap. Here the air gap is larger, whereas here the air gap is going to be really, really small. So whenever the poles are protruding, we call that as salient pole rotor. So cylindrical pole rotors are generally used in high-speed synchronous machines, whereas salient pole rotors are generally used in low-speed synchronous machine, because if you are going to have this rotating at a very, very high speed, mechanically there can be some kind of deformation that takes place along these protruding portions. So that is really not good, especially at extremely large capacity motor drives. So cylindrical pole rotors are generally used in high-speed synchronous machine, whereas salient pole rotors are used in lower speed synchronous machine. What we mean by high speed is maybe 1500 or 3000 RPM if we are talking about 50 Hertz supply, whereas this will be of the order of 300 to 500 RPM. That is good enough for this salient pole structure. Low speed motors will work perfectly fine. That is not a problem. The second type of synchronous machine, apart from wound field synchronous motor, the second type of synchronous motor is permanent magnet synchronous motor. The second type is permanent magnet synchronous motor. So as the name indicates, rather than creating a magnet, electromagnet by supplying field current, so we may supply, in this case, all these currents will be probably dot, and all these currents will be cross. So this is going in and this will be coming out. So this is the return path for the current, whereas this is going to be the forward path for the current. So this is the way the currents are going to flow in the case of wound field synchronous machine, whereas in permanent magnet synchronous machine, there is no field current because you're going to have the magnetic flux created by permanent magnets. Magnetic flux is created by permanent magnet. So the permanent magnet, if we look at it, the structure can be somewhat like this. Let us say this is the stator, and inside I'm going to have the rotor. This is the rotor. So the rotor actually can have rather than having a cylindrical structure, I can draw it somewhat like this. So this is my stator and the rotor can be somewhat like this. So I can have, this is the, if I say this is the rotor, I can have North Pole stuck on the surface like this and South Pole stuck on the surface like this. So I can have basically permanent magnet stuck into the rotor structure itself. And this can be North Pole and this can be South Pole, and it could be glued basically to the surface of the rotor. On the surface of the rotor, it can be glued. So this kind of magnetic arrangement is known as surface mounted permanent magnet rotor. It is actually just mounted on the surface, and surprisingly, the magnetic material itself has pretty high reluctance, just like how the air is having reluctance. Here, the air is there. The air will have high reluctance. The permanent magnet material, although is providing magnetism, that also the material has high reluctance. So the reluctance seen here will be completely uniform. Between the stator and rotor, there will be exchange of magnetic lines and the magnetic field lines, and the reluctance is going to be uniform throughout the air gap. Whereas if you look at the cylindrical rotor machine, in the wound field case, if I am going to have stator like this, the rotor is also cylindrical. So the air gap will be uniform in this case. So air gap in cylindrical machine will be uniform. Because air gap is uniform, the reluctance offered, whether I am looking at anywhere along this, circumference, everything is going to be, reluctance is also a constant or uniform. Reluctance is uniform. So the stator winding, if I try to look at the inductance that is visualized on the stator winding, that will also be uniform throughout. So if I say stator winding inductance or reactance, that is uniform. It is not going to be, different at different points. Whereas if I am looking at something like this, where I'm going to have the magnet somewhat like this, and around this I'm going to have, let us say, the stator. So let me erase this. And let's say I'm going to show this as the rotor, and I'm going to have the stator which is around this. So clearly, the air gap is going to be minimum here. So this is air gap is minimum. Whereas air gap is maximum here. So if I say along the magnetic poles, the air gap is going to be minimum, and perpendicular to the magnetic pole, we are going to have the air gap to be maximum. So we call this axis along the magnetic pole, we call that as D axis. And we call this axis, which is perpendicular to that, we call that as Q axis. So along Q axis, we are going to have reluctance higher. So along D axis, we are going to have reluctance to be lower. So when the reluctance is higher, we are going to have correspondingly, if I try to look at what is the kind of reactance or inductance I have, it is LQ, and this is going to be LD. So LQ is going to be smaller as compared to LD in a salient pole machine. So if I look at salient pole machine, always I'm going to have LQ less than LD. Whereas if I try to look at cylindrical pole machine in wound field rotor, we are going to have LQ equal to LD because there is no variation in the reluctance. So due to which you are going to have reluctance is not changing. So the reactance or inductance will also be uniform along direct and quadrature axis. But if I try to look at the surface mounted permanent magnet motor, we can see that all along the air gap is going to be uniform. So in this case also LD and LQ are one and the same. So uniform reluctance and uniform inductance for the stator winding. So this is essentially the structure of a surface mounted permanent magnet machine. Whereas there are other types of structures also. So here the pole is protruding. The magnetic material or magnetic pole is protruding. Whereas you can have this magnetic pole to be somewhat put inside. So if let us say this is the stator structure and I'm going to have the rotor somewhat like this, I can have the magnet completely put inside like this. I can have the magnet put like this. So here the magnet is actually buried or put inside somewhat. It is inset. So the magnet is inset. Although it is on the surface, it is visible from the surface, it is inset. So mechanically, this structure is stronger. So this is a stronger structure. So you would not see the magnet simply being thrown out or something like that when it is running pretty fast. Whereas here, this is definitely a weaker structure because the magnets are held together only by some glue. And by chance, if it is running at a very high speed, the magnet can be thrown out. So in that sense, it is not as strong as the inset, uh, permanent magnet motor. The third type, what we talk about is buried or interior permanent magnet rotor. So in this particular case, if I am going to have the stator somewhat like this, I'm going to have the rotor here and I will see that the magnet is buried inside. So this will be North Pole and this will be South Pole. So this has to be planned right at the time of construction itself. You cannot suddenly put a magnet or glue it inside. So this will be, in this particular case, if this is North Pole and this is South Pole, the same way here we are going to have this as North Pole and this as South Pole. So the magnet is buried inside. When the magnet is buried inside or the magnet is inset, in these cases, if you look at it, all this place is all iron, whereas this is permanent magnet. The same way, here also, we are going to have permanent magnet inside, but rest of the portions are going to be iron. This is all iron. So iron has generally much lower reluctance compared to the permanent magnet material or air. So along the d-axis, this is the d-axis. Along the d-axis, you are going to see that the permanent magnet material is going to have more reluctance. And along the q-axis, this is the q-axis. And along the q-axis, the reluctance is lower. So reluctance is lower, so inductance is higher. So in this particular case, in a buried or interior permanent magnet machine, IPMSM, interior permanent magnet synchronous motor. So this is interior permanent magnet synchronous motor. So in interior permanent magnet synchronous motor, you will see that LQ is greater than LD because of the presence of permanent magnet. The reluctance will increase along the D axis, which means inductance LD is lower. So LD is going to be lower in the case of interior permanent magnet machine. So in general, the permanent magnet machine, if you look at it, because you don't have to give windings from external power supply, the DC supply from the external power supply need not be given to the field windings. We really do not need this brush or slip ring. So that is the reason why permanent magnet machines in general, permanent magnet synchronous motors are much more rugged, are more rugged, stronger than wound field synchronous motors. But in permanent magnet synchronous motor, it is going to be really difficult to control the excitation or field flux, whereas in wound field synchronous motor, you will be able to control the field flux by appropriately adjusting the DC current. That's not a problem. Whereas field control is going to be really difficult in permanent magnet synchronous machine. There is another type of synchronous machine which is known as reluctance rotor or reluctance rotor type. So in reluctance rotor, what is really the difference is you're going to have the stator again as a cylindrical structure. Three-phase winding will be there, all that will be there. But the rotor is going to be basically something like I'm going to carve at least some portion out from this rotor structure. So I'm going to have this as cylindrical, this also as cylindrical, but in between I may carve out some portion so that I can make this pole look like a salient pole. I'm not going to have any winding whatsoever within this rotor structure. I'm not going to have even permanent magnet. So I just have protruding rotor structure. So you can see this is one pole and this is the second pole. And it is not having, there are no windings or no permanent magnet in the rotor. Only thing is, because there is a revolving magnetic field here, this rotor structure, because it is salient, this is going to get attracted. There is no directionality because North Pole and South Pole are not there. It's not like if this is this is North Pole, it will be repelled by another North Pole, but there is no directionality clearly. So if there is a revolving magnetic field here, this is going to simply attract whichever is the closest pole that is available. So this is essentially no flux available from rotor side. Only stator creates revolving flux. So it is essentially because the ferromagnetic material, the rotor is made up of ferromagnetic material. So this will be made up of iron or steel or something like that. This is going to be attracted by the magnetic field that is created in the air gap. So that is the only way this particular machine works. So this is one of the cheapest machines because you don't need permanent magnet, you don't need windings. There is no worry about either the permanent magnet, which is stuck inside the rotor, or the windings being thrown out when the reluctance motor is running at a very high speed. So in that sense, it's a very rugged structure. So the structure is really rugged and it is inexpensive. But only thing is the flux is available only from one side. So because of which there could be limitations of the torque production. How much torque can be produced by the reluctance machine, that can be questionable. Okay. So to summarize, there are three types of synchronous machine. One is wound field, where the field itself can be controlled. The excitation can be controlled. The second one is permanent magnet synchronous machine, where it is difficult to control the excitation, but the flux is available from both stator and rotor sides. The third one is the reluctance type, where there is no flux from the rotor side, there is only flux from the stator side. So the stator, what you supply is normally three-phase electricity. The flux is created only from the stator side, like what happens in an induction motor. So this particular machine can work only in lagging power factor, because it has to supply the magnetizing current also from the stator side. Stator side is having a three-phase AC supply, and that three-phase AC supply has to supply both the reactive power requirement for creating the flux, air gap flux, and it also has to supply the current which is required for generating the torque. So that is the reason why it can work only in lagging power factor. Whereas in the case of a permanent magnet rotor as well as wound field rotor, depending upon how much current I am supplying from the field, whether it is sufficient to create the entire amount of flux, in that case, you would be able to supply only the torque producing component of current from the stator, which means it can be unity power factor current. So power factor can be controlled by adjusting field current or flux producing component of current. By adjusting the field current, we would be able to control the power factor in the case of a wound field synchronous motor. So one major advantage of synchronous motor, especially wound field synchronous motor, power factor can be controlled. It can be made to completely go from lagging to leading very nicely, very smoothly by adjusting the excitation. Whereas if you look at the induction machine, it will always have lagging power factor. In fact, the best power factor you can obtain in most of the induction machine will be 0.8 or 0.85 lagging. That is the maximum you may be able to obtain as the highest power factor. Whereas in synchronous machine, you can go up till unity power factor or leading power factor. That is not a problem. So when you control the power factor, one of the major advantages you get is, let us say I have a 1000 kilowatt or 1 megawatt let us say 400 volts, synchronous motor. So here I can calculate the current as 1 multiplied by 10 power 6 divided by root 3 times 400 multiplied by cos phi. So this is going to be the current. And cos phi can be unity. So if cos phi is equal to 1, then I calculate certain current, let us say I synchronous machine. This is going to be the synchronous machine current. Whereas if I am looking at an induction machine, so if I want to calculate what is the current for an induction machine, I have to write 1 multiplied by 10 power 6 if it is again, 1000 kilowatt induction machine. So it is going to be 1 multiplied by 10 power 6 divided by root 3 times 400. And cos phi at the most can be only 0.8 or 0.85. So we are going to have basically I induction machine is going to be 0.8 times I synchronous machine divided by 0.8. That is what is going to be I induction machine. So I'm going to have only about 80% of induction motor current will be synchronous motors current. If the current is lower, then correspondingly I square R losses will also come down in the case of a synchronous machine. So if I am looking at, let us say, I have an inverter, then I'm going to have from inverter a long three-phase cable is going along the industry premises, and then I'm going to have a motor connected here. If I'm going to have this motor to be a synchronous motor, first of all, I can control the power factor and make it into unity. So the inverter rating will also come down. So inverter rating can come down because the current requirement becomes smaller. So inverter rating can come down. That is one thing. And I'm going to have lower losses. So both these things are true only for synchronous machine. These are true for synchronous machine. So this is one reason why synchronous machines actually have a better efficiency. So synchronous motors have better efficiency. And power factor can be controlled. So inverter rating can come down. As compared to an induction machine. So these are major advantages we look at whenever we are talking about especially either electric vehicle application where every percentage efficiency matters. Every percentage efficiency matters. So from, let us say 94%, if you take it to 95%, correspondingly, you can reduce the amount of battery you are installing within the electric vehicle. And battery is the heaviest and costliest component in an electric vehicle. That is one reason why, although Tesla car and other many vehicles started with induction motor initially because induction motors are maintenance free. Looking at the reduction in the battery, what you can do with synchronous machine, now people have completely migrated to synchronous motor. That is one reason why electric vehicles generally employ only interior permanent magnet synchronous motor. Another major thing is wherever we are talking about greater than a few megawatt capacity. Induction motors generally work until maybe 2 or 3 megawatt, not more than that maximum. So if you have more than a few megawatt capacity, synchronous motors are the only choice. You don't have an induction machine which is beyond about 3 megawatt capacity or something. Whereas synchronous machines can be built for 200 megawatt, 300 megawatt. We see generators which are 500 megawatt generators, synchronous generators. So they can be built for extremely large capacity. That is not a problem at all. So that is another advantage of synchronous machine. The third one is if we are looking at, let us say, tens of megawatt capacity synchronous machine, even if the percentage efficiency varies by 0.5 or 0.7%, out of 10 megawatt capacity, even if you increase the efficiency by a few percentage, that itself results in huge amount of energy saving or power saving. So even slight increase in efficiency can save a lot of power. So for all high capacity drives, we generally employ only synchronous motors. And another major advantage is the speed is always equal to synchronous speed, which is determined by the frequency. So this is determined by frequency. So you would be able to control the speed very, very accurately. So if you want to control the speed very accurately, like a tape recorder or, like in the case of a clock or microwave turntable, all these things generally will be using synchronous motor wherever you want very, very accurate control of speed. So the major advantages, whatever I talked about, one is synchronous motors always give better efficiency. Second is power factor control. The third one is high capacity motors available. It can be easily applied for high capacity applications and accurate speed control. So these are all typically why synchronous motors are employed in many of the high capacity or very accurate applications. Whenever we talk about such applications, synchronous motors are the primary candidates in many of those applications. There are also disadvantages. There are some disadvantages in synchronous motor. One thing is they are much costlier than induction machine. And if we are talking about wound field motor, then wound field synchronous motors are not as rugged as induction machine. Generally, they are not going to be as rugged as induction machine. And until the variable frequency inverters came into existence, it was not possible to change the frequency. And if you cannot change the frequency, you cannot control the speed of the motor. So inverters are the only means to control the speed of asynchronous mode. You cannot control the speed of a synchronous motor unless you use inverter. So the speed control generally becomes complex. Speed control technique is complex. And in induction motor, once you give a three-phase supply, it is going to start immediately. You don't have to have a starting mechanism. Whereas in synchronous machine, synchronous motors are not self-starting. You need to necessarily give some kind of starting jump start that is important. So some starting technique needs to be employed. So these are the disadvantages of synchronous machine. So in the next class, what we are going to see is, first of all, we will look at starting techniques for synchronous motor. So we are going to look at different starting techniques for the synchronous motor. Then after looking at the starting techniques, then we are going to look at uh, mm, what is meant by hunting. Because when we talk about starting technique, we will be also talking about something called damper winding. So what are hunting oscillations? We will talk about that. And we also will talk about power equation or power angle relationship for synchronous motor. After looking at power angle relationship and hunting oscillation, we will also look at V and inverted V curves. In fact, for deriving the power angle relationship, we will also need to look at equivalent circuit of a synchronous motor. So what we are going to do is, first of all, derive the equivalent circuit. Then we will derive the power equation. Then we will talk about hunting oscillation, otherwise as well as V and inverted V curve. And after doing these things, we will formally go into starting methods with variable frequency supply. Then we look at speed control. Then we will look at braking of synchronous motors.